approximately halfway in this course on signals and systems. This is the 20th lecture and our projection is 40. We want to complete the course in about 40 lectures. It could be plus minus 1 or 2. And today's topic is solution of some problems, major problems in minor 1 examination, and a further look into the properties of discrete time Fourier transform, DTFT. The problems in the minor where the first problem was that the response of a linear system to an input x of n is y of n, which is the sum of x of k, where k goes from n equal to minus 3 to n plus 2. And the question was to find h of n. Now, some of you, this is what I call major problem. Some of you identified this as xk, h of n minus k. Then you wrote expression for h of n minus k and found out the correct answer. This is again a roundabout because you can see that h of n is the response to delta n, and therefore it is simply delta k, where k goes from n equal to n minus 3 to n plus 2, and therefore this is delta n plus 2 plus delta n plus 1 plus etc. plus delta n minus 3. That's it. This is h of n, and in terms of a picture, we start at minus 2. We start at minus 2 and go up to plus 3. So minus 2, minus 1, 0, 1, 2, 3, and each of them is 1. That's it. The level is 1. That's the answer. It doesn't require anything else. It's simply substitution of x of n by delta n. Then the question is the system causal? Now, many of you have answered this question. I have not deducted any marks, but many of you have answered the question by saying h of n is not equal to 0 for n less than 0. Well, this criterion of causality applies to LTI system. So before you prove that it is a time invariant, stating this is not correct. On the answer to the question should have been straightforward by saying that y of n depends on future inputs, because as you can see from this relation itself, y of n depends on x of n minus 3. That is what would be applied y of n depends on x of n plus 2, what would be applied 2 samples later or 2 instances later, and therefore obviously the system is non-causal. Is it stable? No sophisticated stability test is needed, because h of n is simply the sum of delta functions, and how many of them are there? 6 of them to be precise, minus 2 to plus 3, and many people have written there are 5 samples, which is not correct. You start from 0, count up to 5, you have counted how many? 6 numbers. So there are 6 of them, and obviously summation h of n is simply equal to 6, which is obviously less than infinity, and indeed the system is stable. And finally, the tricky question, whether it is time invariant or not. Well, various proofs have been suggested, but the correct proof would be this: x of k equals n minus 3 to n plus 2. Now, this is the input is x of n and the output is y of n. If you want x of n to be delayed, well, some of you delayed the limits. That is not correct. It is not correct to write here n minus n0. The actual output should have been summation. These are independent of what you apply. The summation limits. So summation is k equal to n minus 3 to n plus 2. What should have changed is, instead of x of k, it should have changed to x of k minus n0. and this, as you can see, y1 of n, now follow this point carefully, k equals n minus 3 n plus 2 x of k minus n0. The summation happens to remain unchanged if we replace this by x of k and add here n minus n0. It is the same, and therefore this is equal to y of n minus n0, which means that the system is indeed time invariant. You see, the logic of the argument has to be proper, it has to be correct. The other way, it is not correct. As soon as you attack the limits, well, the limits are properties of the system. It is not a property of the input. It is the input which has been delayed. The system properties have not been delayed, and therefore it is not correct to write right from beginning that k goes from n minus n0 minus 3 to n minus n0 plus 2. What you should write is x of k minus n0. And this completes question 1a. Question 1b is slightly tricky, and this is one example in which illustrates that a picture is worth 1000 words. Whoever has not done it with a picture, 90% of the cases there is a mistake. But let me show you how this problem is solved with the help of a picture. The problem is, find y of n, which is the convolution of x of n and h of n, where x of n is equal to summation k equals minus infinity to plus infinity delta n plus kn, and h of n is equal to a to the n u of n, where mod a is less than 1. The question is, first you have to find out y of n, an expression for y of n. Then you have to answer the question, is y of n periodic? Is y of n periodic? If so, what is the period? If not, give reasons why it is not periodic. Now, obviously, x of n is periodic. If you look at x of n, it is a chain of delta functions, discrete time delta functions occurring at small n equal to 0, small n equal to plus n, small n equal to plus 2n, and on the left hand side small n equal to minus n, minus 2n, and so on and so forth. So, if I plot x of n, which is summation delta n plus kn, k goes from minus infinity to plus infinity, the plot looks like this. We have 1 at n equal to 0, this is n, then 1 at small n equal to capital N, 1, I beg your pardon, 1 at minus n, and this repeats. This is the picture of x of n, the input. Obviously, the input is periodic and the period is capital N. All right. The period is capital N. The question is, if a periodic input is applied to a system, the system response is h of n is a to the n u of n. This is the system response. System impulse response. The question is whether the output shall also be periodic or not. Let's look at it pictorially, and you see the simplest thing to do was to draw a picture. As soon as you put h of n equal to this in the convolution relation, you get a function, an infinite summation of step functions, and it's very difficult to see what actually is happening. Despite writing a step function, one or two of you have come up by some trick with the correct answer, and I must give credit to them. All right. H of n, let's look at h of n. H of n is a to the n u of n, all right, and therefore h of k, you see, in the convolution will require h of n minus k. So let's see what these are. H of k, obviously the envelope h of k versus k, the envelope shall be a decaying exponential. It will start from n equal to 0, k equal to 0, and then go to infinity. And therefore, the envelope shall be like this, where we shall have samples at k equal to 0, this is 1, k equal to 1, and the value shall be a, k equal to 2, the value shall be a squared, k equal to 3, value shall be a cubed, and so on. This is the decaying exponential, all right. This is the plot of h of k versus k. Now, if I plot h of minus k versus k, follow this carefully, we shall have a decaying exponential like this, where it will start from 1, then a squared, a cubed, and so on. All right. This is the picture for h of minus k. Now, if I put h of n minus k, obviously the whole picture will either shift to the right or to the left, depending on the value of n. All right. For example, if n is a positive quantity, then the picture will shift to the right. If n is a negative quantity, the picture will shift to the left. Now, let's superimpose this picture on the picture of x of n. X of n, as you know, x of n is a chain of delta functions occurring at n, 2n, 0, I'm sorry, I misjudged the length. I'll draw it again. X of n is a delta function occurring like this, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It must look proper. All right. This is 0, capital N minus capital N. This is versus k, and this is a plot of x of k. All right. On this, I am going to superimpose the picture of h of n minus k, and let us say n is here. Let us say n is here. Then what we shall have is something like this. Its envelope shall fall like this, and we shall have samples like this. This will be 1. The next one will be a. The next one will be a squared. No negative power of a occurs. It's only positive powers. And then a cubed, and so on. This is the picture, and this tells the whole story. Now you can see what the output is. For example, when n equals to 0, then this picture starts from here. All right, and the first sample, first non-zero overlap shall be 1 of xk multiplied by 1 of h of n minus k, and therefore y of 0 shall be equal to 1, the first sample. The next overlap shall occur when the sample size becomes a to the power capital N, and this shall occur here. All right. So I shall have a to the power capital N. The next one shall occur when it is a to the power 2n, and that shall occur at minus 2n. So a to the power 2n, and so on to infinity. That's as simple as that. And therefore, this is a geometric series, and mod a is less than unity, and therefore this is simply 1 minus a to the n. All right, 1 minus a to the n. Okay. Now let's take n equal to 1. If I take n equal to 1, then this sample comes here, and the overlap with small k equal to 0 becomes of not 1 but of a sample of amplitude a, and therefore the first sample that I get, y of 1, shall be a. The next sample shall be the overlap of 1 with a to the power n plus 1, and therefore I get a to the power n plus 1 plus etc. to infinity, and this obviously is a divided by 1 minus a to the power n, and this continues. This continues. That is, let me draw the picture again. What I have is and so on. My h of n minus k is like this. This is 1, this is 1, this is a, this is s squared, and so on. This is capital K equals to 0, capital N minus n. And in a similar manner, we can show that y of 2, the first intersect will be a squared, and therefore a squared divided by 1 minus a to the n. Now, what happens when you go like this? Y of n minus 1 shall be a to the power n minus 1 divided by 1 minus a to the power n. And if I go to capital N, y of n, then it starts from here. That is, the overlap again now is of 1 with 1. Is that correct? Or is it to the left? It is to the right. That is, this comes here. And therefore, the first sample that I get is again 1. And therefore, y of n shall be equal to y of 0. And this continues, y of minus n or y of 2n and so on. And therefore, it is, the function is indeed periodic with a period of capital N. And in general therefore, the expression for y of n, shall be, the denominator is 1 minus a to the n, and the numerator will be a to the power small n modulo capital N. Okay? Small n mod modulo capital N. In other words, y of 0 is 1 divided by this, y of 1, or let's say y of n capital N plus 2 will be a to the power capital N plus 2 mod n. That means it would be simply a squared divided by 1 minus a to the n. This is the correct answer. This is the correct answer. And we did this very simply with the help of a picture. And the time that I took for explaining with the help of a picture is much greater than the time that one has to spend on writing the solution of the problem. If you had drawn a picture, it would have been wonderful. Otherwise what you end up is a to the n, un, star, convolved with delta n plus kn, summation k goes from minus infinity to plus infinity. Not that it cannot be done that way, but you have to think a little bit what happens when this is, for example, a to the n plus kn, u of n plus kn. And it appears that it is a summing up of unit step functions, and therefore most likely it is not periodic. About 43% of the class, I think, said that it is not periodic. Question number 2a. This was simplicity itself. A signal has amplitude and phase spectra like this. This is amplitude. But I will tell you where the major problems are. Major problems are in concept, not in calculations. This is the amplitude spectrum, and this level is 2, and then you have another 2 at 4 and minus 4. 4 and minus 4, this is minus 2, 2, and this is 0. One has not noticed carefully that the abscissa here is small f, the frequency in hertz. And this is the amplitude, and therefore the frequency corresponding to this is twice pi multiplied by f. That means it is 4 pi. This is the frequency. Many of you wrote e to the power j omega j k omega 0 t. What is omega 0? It's given here. The frequency corresponding to this is 8 pi, for this is minus 4 pi, and for this is minus 8 pi. And the corresponding phases are like this. For minus 2, the phase is pi by 4. Then for plus 4, the phase is pi by 2. and the other way around. The phase has to be an odd function, and therefore it is minus pi by 4 for 2 and minus pi by 2 for minus 4. This is the phase diagram. Could you construct the phase diagram from the amplitude diagram? No. The only thing you could construct is the signs. That is, if the phase is positive on this side, it must be negative on the other side, because the phase spectrum is odd. But these values have to be given. What is the value of phase at the frequency 2 Hz and at the frequency 4 Hz? They have to be given. And now it is simply a matter of writing expressions for the spectrum. The expression shall be like this: capital X of omega. Now first take you have to write the time domain expression, all right. So you have to write x of t. X of t, if I start from, let's say, the signal at minus 4, all right, the amplitude is how much? 4. Amplitude is 4. The phase is how much? Minus j pi by 2, and then the frequency term. Frequency term is e to the power minus j 8 pi t. This is the term corresponding to this frequency, minus 4, and the corresponding phase is minus pi by 2. All right. And in a similar manner, you write expressions for all others. And then combine. You see, this is a real signal. Isn't that right? This is a real signal, and you have to combine into sines and cosines. The answer, try to verify this. Answer is minus 8 sine 8 pi t plus 4 cosine of 4 pi t minus pi by 4. You have to get to this expression, time domain. If you leave it in a jungle like this, e to the minus j pi by 2 and so on and so forth, that does not serve the purpose. Question 2b. Question 2b is, there is a signal which is the sum of two sinusoidal signals, cosine of 2t plus 3 sine of 5 pi t. And the question was whether this is periodic or not, and give reasons for your answer. The type of questions which are, the type of answers that are very frustrating to a teacher is that one of you said that one of these signals, this is periodic, cosine 2t. This is not periodic, because it's, no, I'm sorry, it's the other way around. The period of this is 2 pi divided by 2. That is equal to pi. Is that correct? 2 pi by omega 0. And the period of this is 2 pi by 5 pi, and therefore 2 by 5. And some of you said that because the period is irrational, therefore it's not periodic. That's a very irrational answer. The correct answer is that the ratio of the two has to be a rational number. The ratio is irrational, and therefore the given function is not periodic. Some of you took the straightest shortcut. Since it is a sum of two periodic functions, it must be periodic. One could not be more wrong than this. Question 3a. Use the properties of the unit impulse function to evaluate the following integrals. So the question is, evaluate the integral minus 1 to 10 t square plus 1 delta t plus 2 dt. And the answer, as you can see, is 0, because this exists only at t equal to minus 2, and t equal to minus 2 is outside the region of integration, and therefore the integral must be 0. That's very simple. The second one, evaluation of integral, is minus 5 to 15. That's the range of t. Again t squared plus 1. Then summation infinity, n equals minus infinity delta t minus 5n dt. I don't know the variety of answers that you gave because Professor Prasad graded this question, but the thing that should have occurred to you is that this infinite summation is useless except the range of t, which is from minus 5 to 15. And as you can see, the values of n that are effective shall be n equal to minus 1, 0, plus 1, plus 2 and plus 3. And if you do that, then you can break this up into 1, 2, 3, 4, 5 integrals, and each integral can then be evaluated by finding out the value of small t at which the integrand exists. For example, the first one should be minus 5 to 15 t square plus 1 delta of t if n equal to minus 1 plus 5 dt, and this exists at t equal to minus 5 only. It falls within the range of integration.
No, sir. So this is not evaluation. We cannot evaluate. So this was slightly controversial. Should have been 5 minus 5 minus.
Yes, sir.
So that was slightly.
It is at the edge of the.
Very nice. It should have been minus 5
Minus 2, 15 plus.
It wasn't.
and it should have been 15 plus.
We cannot evaluate.
Okay, I am glad you caught that. If it was minus 5 minus, then the value would have been 26. Okay. Similarly, for the other integrals, and the correct answer, if it was minus 5 minus and 15 plus, would be 380. This is the correct answer.
Suppose we have neglected minus 5 and 15 plus.
Settle that score with Professor Prasad.
What's the correct, sir? What's minus 5 to plus 15?
What is your opinion, sir? What is your opinion?
This is ambiguous. The
The
answer is
answer is
ambiguous.
that it cannot be evaluated.
Yes, sir. Mathematical problem.
You cannot change the question.
Minus 5, no, you cannot change the question. You can take from minus 5 minus or minus 5 plus. You get two different answers because the delta function is discontinuous at the point at which it
As such,
occurs.
the integral is not evaluable.
As such, the integral is not evaluatable. Okay. I may be wrong. Question 3b is a holding circuit. Well, commonly used in pulse system is shown in the figure. The figure is x of t goes to a summer plus then minus, and here is a delay t, and then there is an integrator. This is y of t. The question is this a linear system? Well, let's see its input-output relationship. You see that the signal here is x of t minus capital T. So the signal here is x of t minus x of t minus capital T, and this is an integral sign, and therefore y of t is equal to integral minus infinity to t x of t minus x of t minus t dt. That's it. And you see, differencing is a linear operation. X of t minus x of t minus t is a linear operation. So is integration, and therefore the system must be linear. Well, formal proof, a rigorous proof, would require this artifice, that is x12 leads to y12, then you prove that alpha x1 plus beta x2 leads to alpha y1 plus beta y2. All right, which is very easy. It follows from the definition. The next question was, well, obviously it is linear. Next question was to determine the impulse response. Well, y of t is minus infinity to t x of t minus x of t minus cap t dt, and the impulse response means that you simply substitute x of t by delta t, and the result is h of t is equal to minus infinity to t delta t minus delta t minus cap t dt, and integral of delta t is the ut, and integral of delta t minus t is u of t minus t. So it's simply a gate function which exists from capital T equal to small t equal to 0 to capital T. This is 1, 0, capital T. This is ht versus t. What was the reason that the system was supposed to be initially at rest? What would have happened if it was not at initial rest? Pardon me? Time invariance would have been affected. There is no point at which time invariance or time variance is being called for. It's a food for thought, and I leave it like that. Question 4a. Find the exponential Fourier series for the signal x of t equal to sine squared omega 0 t cosine of 2 omega 0 t. You have to find out the exponential Fourier series. Well, the question is, how do you look at it? Do you look at it as general x of t, and therefore you find out, you write x of t as ak summation e to the j k omega 0 t, find ak and all? No, it's much simpler than that. You write sine squared omega 0 t as e to the j omega 0 t minus e to the minus j omega 0 t divided by 2j whole squared. Then cosine 2 omega 0 t you write as e to the j 2 omega 0 t plus e to the minus j 2 omega 0 t divided by 2. Multiply these out and write it in the form of an increasing power of exponential. That is, start from what would be the highest negative frequency? Minus 2 omega 0. Highest negative frequency is 2 omega 0, not minus 2 omega 0. All right, and then omega 0. Will there be a DC term? No. Will there be a DC term? No, because there is a multiplication by, there is a DC term here, but then it will be multiplied by this. The highest negative frequency is not 2 omega 0, 4 omega 0, because of multiplication by minus 2 omega 0 by minus 2 omega 0 here. So you shall have frequencies minus 4 omega 0. Shall you have minus 3 omega 0? There would be a DC term. Where from does it come?
So 2j minus 2j.
Two DC terms. Well, they can be combined into one. Okay, so minus, will there be a term 3 omega 0? Yes or no? No. So minus 2 omega 0, will there be a term omega 0? No. So 0 frequency, then plus 2 omega 0 and plus 4 omega 0. And that's it. You can find out the coefficients. The final problem, question 4b. Now there, I am told that there were major problems in solving this question. It is a cosine omega 0 t, then u t plus t minus u t minus t. So it is a cosinusoidal function. It is this signal a cosine omega 0 t which is passed through a gate extending from minus capital T to plus capital T. So the function looks like this. This is the kind of function that is used in a pulsed radar, a function which is a cosine wave passing through a gate from minus capital T to plus capital T, and it is a cosinusoidal function like this. It's a burst of cosine. It's a burst of cosine functions within a small interval, and the smaller this interval, that is 2t, is, the higher is the resolution of the radar. Radar, as you will learn later, is used to detect objects in the neighborhood, okay, by radio means. Now the question that was asked is, omega 0 is given as 2 pi by capital T, okay. This omega 0 is related to this capital T and minus T, and you have to find out the Fourier transform, that is capital X of omega of this, and then express your small omega, capital X of small omega, alright. Yeah, and then you have to express your answer in terms of the sinc function, and also make a sketch of capital X of omega, mod, that is the amplitude function. And the simplest way of doing this is to apply the definition. Do not try to apply this shift and those kinds of things, you will get into trouble. The simplest thing to do here is to express cosine omega 0 t as e to the j omega 0 t plus e to the minus j omega 0 t, and then this would be e to the minus j omega t dt, alright. This is the Fourier transform, capital X of omega, and the integral shall last from minus capital T to plus capital T, and you shall get sum of two sinc functions, sinc 1 and sinc 2, and the final result well looks like this. Final result looks like this: AT sine of, you can convert this to a sinc, omega minus omega 0 t divided by omega 0 minus omega capital T plus sine of omega plus omega 0 capital T divided by omega 0 plus omega times capital T. That is truly sin x by x form, and if you plot this, then you get something like this. There is no DC. Well, there is a DC, but no, there is no DC, and there is a peak here, and there is a peak here. This peak occurs at 2 pi by t, and this peak occurs at minus 2 pi by t. In between, there are small ripples like this. I don't know, you can plot it. But this is the type of sketch that you get. Any questions on the? In the few minutes that are left, let me review what I did last time. Let me review the 3 or 4 properties. One of the purposes of repetition is to learn. Repetition is an essential part of the learning process. I'll just quickly tell you 3 or 4 properties because I am going to utilize them later. The Fourier transform capital X of capital omega of a discrete time signal x of n is dash periodic with a period of twice pi. So it is periodic. Number 2, it is a linear operation, which we proved. And if x of n is real, then there are several interesting properties. One is that capital X of omega is x star of minus omega. Can you tell me what is the transform of x of minus n? Capital X of minus omega.
Excuse me, xn is periodic in the first case, or is it any general thing?
X of n in the time domain. No, time domain is not constrained at all. Whatever it is, whether it's periodic or non-periodic, the frequency domain it is always periodic, which does create problems. We also know that if x of n is periodic, then real part of capital X of omega, no, I'm sorry, if x of n is real, then real part of x of omega is even, imaginary part of x of omega is odd, and the magnitude is even, angle is odd. And we showed that the even for an arbitrary signal, arbitrary real signal, the even part of x of n transforms into real part of capital X of omega, and be careful now, odd part of x of n, j times imaginary part of x of omega. We also did the time shifting and 1. We also showed that if x of n is real and even, what can you say about capital X of omega? It should reflect the same properties. Now, this in working out problems is extremely useful. We also did a time shifting and frequency shifting properties. Time shifting is x of n minus n0 transforms into e to the power minus j capital omega n0 capital X of omega. And the other thing is that if I multiply x of n by an exponential signal like this, the result becomes capital X of omega minus omega 0. We shall give a final touch to the rest of the properties in the next class. That's all for today.